Good evening, everyone. This is team number one, Anna de Schröedingger. And in this project, we tackle the endpoints problem using mathematical modeling and optimization techniques. So I leave the word to my colleague Rebecca to further explain the introduction.
Well, first of all, what is this problem about? The endpoints problem is a classic problem in both mathematics and computer science. And all it started in 1848, when a German chess player named Max Bessel came up with the original idea how to place 8 queens on an 8x8 chessboard without them attacking each other. That means that 2 queens cannot be in the same row, column, or diagonal. And a couple of years later, in 1850, the mathematician Franz Naut took this idea and extended to boards of size n times n, a problem we know today as the n-queen problem. If you can change, thank you. Now this problem seeks to answer the following question. How can we place n queens on an n times n chessboard without any of them attacking each other? In other words, given a number n, we have to place exactly n queens on the board, being careful that no queen shares row, column, or diagonal with any other queen. This is the part that makes the problem interesting. It's not only about placing queens randomly, but also about finding configurations that follow these restrictions. Now let's continue with the next section.
Let's talk about the methodology of this problem. Why we use dynamic programming? Because it's a powerful method for solving complex optimization problems. The core idea is to break a large complicated problem into smaller and manageable subproblems. Once a subproblem is solved, we store its result and reuse in wherever needed. It's avoid repeating the same calculations over and over, which saves both time and computational effort. Next slide, please. Thank you. How we apply this dynamic programming into the endpoints problem. In our case, we apply this idea was to put solution step by step. Each time we found a valid arrangement of queens, we iterate in a constraint to prevent the algorithm from generating the exact same configuration again. Why? Because the board fluctuation or rotating the board is the same solution. By doing this, we avoided restricting known solutions and focused on only new ones. This approach helped us significantly reduce execution times and improve the overall efficiency and the result. Let's move on to the math model with my partner, Anna.
Okay, so we are going to talk about the mathematical model. First, we have the parameters of the problem. We define the next or the following four: the size of the bar and the number of the queen we only receive as input n. Some other things that are taken into consideration yet are not input are available rows, available columns, and available diagonals. Next, we have the decision variables. There is a matrix. Binary matrix indicate if a queen is at that position or not, and where x subscript I, j, it collocates 1 if the position is occupied, and 0 if the position is available. The object function maximizes the number of possible solutions satisfy the condition, where x subscript k, 1, it collocates 1 if the configuration is valid, and 0 if the configuration is not valid. And we have one point to consider. X subscript k represents a matrix of size n for iteration k. Each element x aj, where x aj is equal for 1 if the queen is placed at row I and column j, and x subscript ij is equal 0 or in other ways. And S is the total number of possible configuration of the possible configuration. The restrictions or constraints, we have 5. no more than the queen in the same row, and we have the mathematical represented. The number 2, there should not be more than one queen in the same column. The number 3, there should not be more than one queen on the same main diagonal. The number 4, what that we define, there should not be more than one queen on the same secondary diagonal, and we need to consider it that K is equal I plus J. Number 5, additional restrictions are added with each feasible solution found, where n is the number of the queens to be placed and the sum represents the cells where a solution was found. Then we are going to pass the next section.
So now let's talk about the code. This problem consists of the optimization of an objective function that maximizes the number of queens that can be placed on a chessboard of size n by n. To solve the model, we use the Gurobi solver to AMPL. Here we select the set option solver in Gurobi, and then we decided to add rotations and reflections to optimize the code. In this way, we can generate all the equivalent forms of the solution for the n-queen problem. As a result, it returns a set of solutions that includes all equivalent variations, a rotation and reflection, removing duplicates by conversion in tuples to be included in a set. This allows an efficient comparison of the solutions. In addition, all of the solutions are stored in a .json file, so we can actually see what the solutions are and interact with them if we need to. The following code cell shows the vertical mathematical model where the variable x of ij indicates if there is a queen in cell ij. It also shows the 4 constraints and the objective function. Since it is a satisfaction problem, an objective function is not strictly necessary, but we still declared it. When a model finds a valid solution, it may be the case that it returns the same solution in the following iterations. This is why we have a block of code in which a new constraint is created and adapted to the current element. Now let's try running the code and see a demonstration.
Well, now that we have seen how the code was developed, we're going to talk about running the code. The code has a data validation to make sure that the user puts an integer for the number n. This number must be greater or equal to 1. In case of typing anything that is not a number greater or equal to 1, the program will display an error message. As we can see in the screenshots below, we have 3 cases. The first one, when the user puts a 0. The second one, when the users input a negative number. And in the last one, when the user puts a letter. As we can see in all of them, the program puts an error message saying that it is an invalid value for the integer n. And it displays an option to the user to put any other value. On the other hand, when the user provides a valid number to the integer n, the code returns the total number of solutions and also the solving sign, as we can see in the screenshots. And it also asks the user if it wants to see all of the solutions. This because when we are talking about a number of queens greater than 10, the number of solutions increases exponentially. So we first ask the user if it wants to see all the solutions. As we see in the example, we have when the number n is equal to 4, and it has 2 solutions, as we can see in the screenshots. So now we are gonna see 2 specific problems. That is when the number, even though the number is correct, it has no solutions. As we can see here, when the number of queens are equal to the number 2 and number 3, there are no solutions, and the code displays the message that says no solutions were found. Okay, now we're gonna run the code in the presentation to see that it actually works. Yes, right there. So to run the code, first of all, you need to run all the cells that are above
the last one so that you can load all the dependencies that are needed. Now that we have run everything, we can put a number to see the solutions. So let's say we want to see the solutions for a number equals 5. So as we see here, it prints the solving time and the number of solutions, and it asks if we want to see all of the solutions. Let's say we want to see them, so let's put an S, and it will display all of the solutions as we can see here. So with this, we can say that the code actually works with any errors. So now let's move back to the presentation.
Okay, well, then that we validate that our code actually works, let's take a look at actual solutions that our code give us. So right there we have the solutions where n equals 4. This is the first non-trivial solution where we have two different solutions. It's as I already said, it's the most easy solution that our program gives us. For the value of n equals 5, we have 10 different solutions, and as you can see in the image of the presentations, we can see all of these 10 solutions. Where n equals 6, it's a special case. It's the only case when the number of solutions actually decrease. When n equals 5, we have 10, but when n equals 6, we have 4. This is a special case. And move on to n equals 7. We can see that the number of solutions jumps to 40 solutions. And right here, we only see the first 4 and the last 4 ones. And for the value of n equals 8, the number of solutions jumps to 92. As my classmates say, the number of solutions increase exponentially. So we have 92 for n equals 8. For n equals 9, we have a number of 352 solutions. And as the previous ones, we are only showing the first 4 and the last 4 solutions. Now for a value of n equals 10, the number of solutions jumps to 724 solutions. And as you can imagine, the number of solutions continues growing exponentially. And finally, for n equals 11, the number of solutions are 2,680 solutions. And we are only displaying the first 4 and the last 4 because it's a very huge number. And finally, as my classmate Arturo said, we stores or saves the solutions in a JSON file where the user can actually see each one of these solutions. Now moving on for the next section.
So the next table shows an overview of the performance of our model for port sizes 1 to 11. For example, we can see that for one queen, the solution is immediate, and for n equals 2 and 3, there is no solution, and also the running time is very slow, very fast. And from 7 queens onward, the solution count and runtime grow rapidly, reaching 2,680 solutions and 36.45 seconds at 11 queens, demonstrating exponential and complexity growth. And this project focuses on maximizing the number of queens placed on a n times n board using a mathematical model. We are using Gurobi through AMPL, and it was chosen for its sustainability for the problem. To enhance performance, we implemented functions that generate symmetries for each solution, and also rotates and reflects the solutions, to prevent the solver to recalculate all the solutions. And also, there is a room for improvement that can increase the efficiency of the program.
Well, now let's go over the conclusions we arrived from this project. As we saw before, we addressed the classical problem of trying to place n queens in a chessboard, and as we know, consists in placing the queens so that no queen can attack each other. And of course, the goal was to develop a mathematical model and implement a solution with code using, as we saw, the Groovy solver through the AMPL platform. And to avoid repetitions, we incorporated filters to detect symmetries, which rotated and reflected the solutions we found, so that the runtime would be less, and we could actually reach more solutions faster. And also, I think this model performed very well on small instances of n, but as we saw, while n keeps growing, the runtime starts growing as well exponentially, and we are going to reach points where we're trying to solve for 12 queens, and the code is going to start running for hours and hours, and our computers may not be able to run for that long. Or if we had better computers, if we had access to better computers, we could actually run it faster. Also, from this project, if we can move on to the next slide, we saw that we have a lot of room for improvement, and of course, we implemented a solution that used dynamic programming, but also other approaches to this problem might be valuable, such as backtracking algorithms. And we implemented the knowledge we learned from the operations research and linear programming courses. And I think this project helped us strengthen our skills. And also, I think it awakened some curiosity for us to keep learning in the future. And it also demonstrated how mathematical modeling and computation tools can be very effective when we try to tackle and solve very complex problems we couldn't possibly do by ourselves. And also, as part of this project, we created a LaTeX file in which we detailed everything we did throughout this project.
Well, as well as my classmate said, we developed an article where we show up all the details of developing this problem. As we can see here, we have a little abstract, a brief introduction saying everything about the n-queens problem. We also have the objectives, both the main objective and also the specific ones. And we have the methods where we specify all the model. As we can see here, we have the input data, the variables, the objective function, the constraints. And also we have all the code development detailed. And we have the running code and the results, as we saw in this presentation. All of the screenshots of the code and a little conclusion. And also in this article, we include in the annexes all the solutions from when the n takes the value of 1 to when it takes the value of 10. As we can see in here, there are a lot of solutions. So the number of pages in the article grows up to more than 90 pages. even though we are putting a lot of chessboards in every page. So, well, we won't see all of them because they are a lot, but they are in the article and you can see them if you want to see every detail of the development of this presentation. So this will be everything for us. Thank you so much for your attention and we will see you soon. Goodbye.
Al final lo exponemos, ponemos, ¿cómo se llama? Esas cosas
Bloopers.
los bloopers,
Bloopers.
sí.
Bloopers. Ana, ¿sí corriste
Pero
todo?
sí lo corrí todo.
En ese código no se muestran.
No, es que ocupamos
está mal entonces. Y
Mm.
ponle otro parámetro que reciba. No. No.
No, hombre, Arturo como profe se muere de hambre.
Bueno,
No,
ahí
es
arriba.
Que es difícil
No,
así.
no, ay no.
Casi
Es
me va a
difícil
regañar,
así.
nada más porque estamos grabando.
We have a number of 3,052 solutions. Applying the first
Córtale ahí. No son
¿Por qué?
3,000, es 300.
300. Yeah, okay.